Here, I'm just going to walk through some different scenarios, working out the nuts and bolts part of the problem with the disk method. We're going to find the volume using the disk method. So these are the four examples we're going to do in this video. I'm going to keep it with the same original equations, the same graph, but I'm going to switch the scenario on it. We're going to revolve that graph about the x-axis, y-axis, the y equals 8 line, the x equals 5 line. So those are the four examples that we're going to do. I just want to remind you from that understanding part of the video, these are the steps that we're going to follow when we find the volume of something using the disk method. And so I'm going to follow these steps. We're going to use this formula. All I'm going to do is set up these problems. I'm going to show you how to find that capital R and the little r, and I'm going to set these problems up. The integrals themselves are easy, so you shouldn't have issues, major issues with the integrals in this section, but it's just setting them up. That's all I want to show you with the new stuff. Your homework responsibility is to set them up and also integrate them, plug in the numbers, work them out, find those exact volumes. But so here we go. All right, so I want to take this shape. So my first step, right, is to draw the bounded area. You can use the graphing calculator to graph that thing, but if you graph y equals 2x squared, that's your whole entire parabola. But you're just going from like y equals, so y equals 2x squared is your whole parabola, and you can put your whole parabola in there, but I know when I see y equals 0, that's my x-axis, and when I see x equals 2, that's this vertical line. So you got to be careful with that. So this is our bounded area right here, okay? And you got to be careful with that, because if I say x equals 0, that's your y-axis, y equals a number, then your bounded area is over here. So you got to make sure you get that correct bounded area. So I draw the area, and I label the points. I know this is 0, 0. I know this is 2, 0. And if I take the 2 and plug it in for x right there, that then give me that y value right there is going to be 8. And so that's what I mean by draw your bounded area. And then I'm also always going to label the axis of revolution. So this time we're going to take this shape and going to revolve it about the y-axis right there. So I'm not sure exactly what you're seeing there. I'm seeing kind of like an enclosed like half pipe sort of deal or something like that, right? But whatever shape you see there, it doesn't matter. I'm going to show you the steps of how we could find the volume of that shape. Okay, so here's the disk method. Here's how it's going to work. So let's follow these steps. We're going to first draw a rectangle perpendicular to that axis of revolution. So there's my axis of revolution. So I draw a rectangle perpendicular to that. So I draw it sideways, and then you're going to determine your dx or your dy. Notice that little part is vertical. All right, the little part, that's the width of that rectangle, that's vertical. That's what tells me this is going to be a dy problem. So I already have 3 steps of our 4 steps now. I got the area, drew a rectangle perpendicular to that, and then remember, if it's sideways, if it's up and down, that's a dx problem. If it's sideways like that, the little part is vertical like the y-axis, which makes it a dy problem there. So I have the first 3 steps entirely done, and no matter how many processes, I've worked out thousands of these problems, guys, and I still never skip over those steps. All right, I get my area, draw my rectangle, disk method is perpendicular. Right now you only know the disk method, so we're just practicing that one thing. So it's going to be perpendicular this section, and I need to determine whether that's a dy problem or a dx problem. All right, so how's the part where we typically will have most of our questions around is how to determine what the capital R is and what the little r is. So the capital R is the distance. So let's kind of read what this says there. Capital R is the distance from your axis of revolution to your farther edge of your bounded area. The little r is the distance from your axis of revolution to your closer edge of your bounded area. So here's your axis of revolution. And when you go to the farther edge of your bounded area, you're way over here. So from your axis to your farther edge, that's what the capital R is. And when you're going from straight edge to straight edge, if I said, what is this distance from the axis of revolution to that x equals 2 line, every single time, that straight edge to straight edge, that's the same number every single time. So if it's the same every single time, that means we can use a number for that, no variables. And so I can say that capital R is equal to 2. And then what your little r is a distance from your axis of revolution to your closer edge of that bounded area. So you're measuring from your y-axis over to that curve. And see how that's different every single time? So if it's different every single time, that means you can't use a letter, you can't use a number for that. You got to use a variable for that. All right. So anytime you measure from the y-axis over, that variable that you're going to use, you're going to start off with, that's just x, okay? Because think about this, like if I said, what's the distance from here to here, we know that's 2 units. But then if this is from here to here, if this x value is 1.7, that's what that distance is. If this x value is 1, that's what that distance is right there. So it depends on what that x value is along the curve. So we'll start off like that. And I'm gonna use that same thinking when we do the next section as well. So it starts off with that, and then here's the deal. If this is a dx problem, I get to stop right here and I get to use that single letter, that single x in my formula. But since this is a dy problem, we need to change it, okay? So we notice how we got this y equals 2x squared. I'll use this if it's a dx problem, but then I need to solve this for y, or get x in terms of y. So if I solve that for x, I'll get x equals, I'll move the 2 over, square root both sides. I'll get x equals the square root of y over 2. And I know I'm over here there, so I'm using that positive value there. So since this is a dy problem, I got to solve that in terms of y. So I'll use x equals that square root of y over 2. That's the hardest part of the problem, is just coming up with the capital R and little r. Once you see it, it's gonna be easy for everybody there. But sometimes people bomb a test over this and then they realize that it's easy there. But this is something that's on every single AP test I've ever seen. Something in Calc 1 and Calc 2 in colleges is just good for college prep. It's good for the AP test as well. We'll get plenty of practice with this, and you just gotta practice to where you're perfect with it and you can't mess this stuff up. All right, so here's what we'll do. Once you get your capital R and the little r, like I said, that's the hardest part. Now you're going to just use this formula. All right, so when you use your disk method, you're just gonna have the pi guy out in front, and then you're gonna have the integral. You're gonna do capital R squared minus this little r squared. And then it's a dy problem, so I squeeze that in there. Now, if it's a dx problem, use the x's, go left to right, that take you across your bounded area. So if it's a dx problem, I'm gonna go 0 to 2. And then if it's a dy problem, everything in terms of y, which means the numbers attached to the integral have to be in terms of y. So you use the y's that take you across your bounded area. So bottom to top, when it's a dy problem, you go bottom to top like you're doing a range. Your lowest y value is 0, and then you're gonna go up to your highest y value of 8. So that's with any dy problem. All right, those are the y's that take you across the bounded area right there. And so there's your setup. Now, if I just ask you to set it up, that's all you would have to do. So the homework, you're supposed to set them up and you're supposed to integrate it. On a testing situation, I may just ask you to set it up. That's all you would have to do. You wouldn't have to actually work it out or simplify it all. But I think we all realize that this is an easy integral. That's just going to be 4 minus, when you square root that square root, that's just 1/2 y. And then you see how easy this integral is right here, but we got to make sure we set those up with the pi out in front, with the correct numbers attached to integral, the correct inside, and you got to have that dy or the dx on in there. So if you have it, do just actually set up my test over that, you got to have it like that perfectly. If you want to simplify it, you can. But if you simplify it and you make a mistake doing that, then I got to deduct for that. But I think we all realize as we're doing the homework, this is a pretty easy integral, all right? So the integrals themselves aren't really that complicated, this chapter right there, because we're just kind of showing you that new stuff right there. So I'm going to go on. It's more important for me to just show you as many scenarios as possible. And so I'm just going to stop right there. But your homework, you could just work that out there. All right, now we're going to move along. All right, notice what I already have set up for you. I strongly suggest you do a picture for each different scenario. If some of you are be good at doing one picture, and you can use that single picture for all 4 scenarios when you have to do these different parts there, it helps me. Even sometimes I might do one picture with it all labeled really, really good. And sometimes I might just do a real rough sketch, maybe not even need to include the labels because I already have the labels in front of my face right there. But I always like to have a separate, different picture that I could draw my stuff on. So I suggest that you kind of do that. Sometimes people, when they bomb the test, they're not doing that. And then I suggest that, and then they do a lot better like the second time that we do something over there. All right, so let's just do a different scenario. All right, so we're going to measure now, use the x-axis as our axis of revolution. So I have my bounded area drawn, I have it labeled, I have my axis of revolution labeled there, and this method is the only method we know at this point there. So when you find the volume of the disk method, so we're going to take the shape, revolve it about the x-axis there. So I'm seeing like a trumpet sort of deal, or like a sorry game piece. You know, I like that game play sorry there. Get that blue sorry game piece going on. But whatever shape you see there, we're going to find the volume of that shape. All right. And notice that it is a different shape than this guy. So that axis of revolution does make a difference. What we're doing here, we're going to get different volumes of different shapes there. Now, disk method, we draw a rectangle perpendicular to that axis of revolution. And then I notice that that little width part, that little part is horizontal, like the x-axis is horizontal. So that's going to be a dx problem. So my first 3 steps are completely done. I have my area, I did perpendicular, and I got that that's a dx problem right there. Now I'm on the part where we're going to find the capital R and the little r. So the capital R is the distance from your axis of revolution to the farther edge of your bounded area. So here's our bounded area, this inside part. You're measuring distance from the x-axis up to your curve. And see how that's different every single time? So if it's different every single time, you got to use a variable for it. Now, what variable we're going to use, this, when you measure from the x-axis up, if I say like, what is this distance from here up, you guys probably would tell me 8. That's that y value right there. So if this y value is like 7, that distance is 7. If this y value is 3, that distance from the x-axis up is equal to 3. So whenever you measure from the x-axis up, that variable always starts off as y. If this is a dy problem, I get to use that single letter. But since this is a dx problem, I have to use the x version of what that y is equal to. So y is equivalent to 2x squared. So I need to switch that to 2x squared. The little r is the distance from your axis of revolution to your closer edge. So if this is your axis of revolution, is your x-axis. When you're standing there going, this is your farther edge, is your curve. Your closer edge, you're standing right on it. Your axis of revolution, your closer edge are exactly the same thing. There is no distance apart. Like if my axis of revolution would have been down here, I would have had a little distance from the axis of revolution to that closer edge, to that x-axis. But my axis of revolution is right there. The axis of revolution and your closer edge are exactly the same. There is no distance between them. So that means the little r is equal to 0. That just means when you revolve that shape, that sorry game piece, it doesn't have a hole in the middle of it. So that little r is going to be equal to 0. So when you set it up now, so I found my capital R, my little r. Now we're just going to go to this formula and we're just going to set this thing up. So the disk method has a pi guy out in front. And then we're going to have capital R squared minus the little r squared. This is a dx problem. Now, if this is a dx problem, these numbers attached to the integral are the x's that take me across the bounded area. So go left or right like you're doing a domain. What are the x's that take you across your bounded area? And so you're going to go from x equals 0 to x equals 2. And so if I ask you to set it up, I mean, you wouldn't even need to include that 0 right there, but it always helps me to write this stuff down. Write down what they are and then go to your formula right there and then to kind of see the different pieces there, give you as much partial credit as we can. But if I just ask you to set it up, you can just stop right there, right? But when you're working it out, you realize that this is a really easy integral. That's just going to be 4x to the fourth, right? Integrate that sucker, plug in the 2, plug in the 0, and that's going to give you the exact volume of that three-dimensional shape right there. All right, let's do 2 more scenarios. We're doing all 4 big scenarios. These are our 4 main scenarios all in one video here. All right. So this time we're going to take this bounded area. We're going to revolve it around that y equals 8 line. All right. So that's going to create some three-dimensional shape there. Whatever you're seeing in your head, we're going to find the volume of it. But you don't even have to see what the shape is to find the volume of it. But let's make sure we really focus on these different axes of revolution there, because sometimes people struggle with getting the capital R and little r right there. So the same thing. This method is the only method we know. So I'm going to draw a rectangle perpendicular to that axis of revolution. So it's going to go up and down. So it's perpendicular to that y equals 8 line. And I notice that that little part is horizontal again, which means this is going to be a dx problem. So my first 3 steps are entirely done. And now we're just going to come up with the capital R and the little r. All right, so your capital R, again, say those steps in your head. It's the distance from your axis of revolution to the farther edge of your bounded area. So you're standing right there on your axis of revolution. Your farther edge of your bounded area is the x-axis. You're measuring from this y equals 8 line to that farther edge, the x-axis. And notice that you're going from straight edge to straight edge. That's the same number of units every single time. That's 8 units every single time. And so I get to use a number for that because that's not changing. Now here's the tricky part. The little r is a distance from your axis of revolution to your closer edge of your bounded area. So your closer edge is this curve right here. And notice that that's different depending on where you're at, right? So if it's different every single time, we can't use a number for that. We have to use something with a variable or a variable expression. And so I want you to just think for a second what that could possibly be. Sometimes we see that right away, sometimes we don't. It has nothing to do with calculus. It's all about just basic, not really common sense, because sometimes it gets a little tricky there, but it's just basic geometry, basic measuring stuff there, okay? If I said, I want to know what is this distance right here, okay? Here's what we just talked about. We talked about on this problem, when I measure from the x-axis up, it's whatever that y value is. So when I measure from the x-axis up, that was our variable y. I don't want that distance. I want the rest. I want the distance from here down right there. Now, if you think about it, the whole darn thing from the axis of revolution to that x-axis, the whole darn thing is equal to 8. So this whole line is equal to 8. And I don't want this y value right there. I just want this part that's left over. And so that's going to be the whole darn thing of 8. And then we're going to subtract out that y. So again, your distance from the x-axis up, that's whatever that y value is. So if that y value is 7, this distance is 7, but I want the distance from the axis of revolution to the closer edge. So if that was 7 that way and the whole thing is 8, I'll go 8 minus 7. That means that's equal to 1. So that's just changing throughout there. So that's just kind of like basic measurement things that we're going to use right there. So I would hope that we understand that. I'll probably talk about that in the next video, in the next section, how those are coming about. But you could also just kind of have memorized whenever you measure from the axis down, it will always be that number minus y. So we start with that thinking. Now, I know I keep saying this, but it's going to make a difference once we put the disk method and the shell method together and we have different techniques there. But if this is a dy problem, I get to use this 8 minus y. That's why I always start with that. I don't shortcut that. Even if we are changing or not changing, I always start with that and I write that down because we always won't need to change it. It's just going to seem like it right now until we get the other technique under our belt, right? So I start with that. If this is a dy problem, I get to use the 8 minus y. But since it's a dx problem, I have to convert that y in terms of x's so that y is equal to that 2x squared. So that's the hardest part of the problem, is just coming up with these. Once we get good at these, you'll know when you're ready because you'll be perfect with them. And that's really what we got to study the most, is just coming up with those capital R and the little r right there. All right, to where we're just perfect with that and become experts at that. All right, now when I set it up, the disk method, we got the pi guy out in front. And we're going to go capital R squared minus the little r squared. This is a dx problem, which means we use the x's that take us across our bounded area. The numbers attached to the integral have absolutely nothing to do with where that axis of revolution is at. It's only with your bounded area. You can't integrate beyond your actual area. So on every dx problem, on this particular problem, no matter what that axis of revolution is, all right? I use 0 to 2 right there. Those are the x's that left or right that took me across the bounded area. I'm gonna also use 0 to 2 right here. Those are the x's that take me across that bounded area. That 8 is being handled inside that thing, but your bounded area, you can never integrate beyond your actual bounded area right there. So sometimes when I have to do a bunch of scenarios on something like this, when I do my initial graph, I'll just make a note for myself. I'll just jot down, hey, on a dx problem, I'm gonna be integrating that sucker between 0 and 2. On a dy problem, I'm gonna be integrating that thing between 0 and 8. And then I don't have to think about it anymore. I just know that it's gonna go 0 to 8 if it's a dy, 0 to 2 if it's a dx, because those numbers attached to integral have nothing to do with your axis of revolution, all right? And then might be wondering, I did forget to put my squared right there. That's gonna make a big difference there because now I got my capital R squared minus the little r squared. So if I just ask you to set it up, that's got to be like that, right? You got to have the pi guy out in front. We got to have the numbers attached to the integral. You got to include that dx or the dy. They're going to want that. So on the AP test, sometimes these will be on the calculator part, sometimes it'll be on the no calculator part. A lot of times they might just ask us to set something up. And then sometimes they'll ask us to set it up, sometimes they'll ask us to work it out. But I just need us to be perfect with the setups, because the nuts and bolts part of like working it out, we might make a little mistake here and there on there. But if you got your setup, you instantly have like a chunk of points right there. And then if we make a little mistake when we're actually working it out, we're going to be okay. We're going to fix those things. Those kinds of mistakes are going to fix themselves. But you must be perfect with getting those values and getting that set up right there. All right, and then the last scenario, we're going to go about the line x equals 5 here. And so there's my bounded area. I already drew that graph. I got my labels on there. And then here's my axis of revolution. So I did my little symbol there. And then I'm going to find this volume using the disk method. So we're going to draw the rectangle perpendicular to that axis of revolution. Remember, that rectangle represents one of those circular disks that we showed you in the understanding video there. And notice how it's perpendicular to, it's perpendicular to that axis of revolution right there. And then notice that this little part, the width, is vertical, like the x-axis, the y-axis is vertical. That's going to be a dy problem. Please don't skip over those steps right there. All right, and now we're to the point where we're going to find our capital R and the little r. So very similar thinking that we talked about here. Let's do the little r first. Your little r is a distance from your axis of revolution to the closer edge of your bounded area. So if you're going from here to your closer edge, notice that straight edge, that's from 5 to 2 every single time. That's equal to 3. That's your closer edge. That's your little r, and that's the same every single time. Your capital R is the distance from your axis of revolution to your farther edge. So you're measuring from here to that curve, here to that curve, here to that curve. And see how that's different every single time, which means I can't use a number for it. I got to use something involving a variable. So it's very similar to what we talked about right here. If I said what this whole distance is, so if I extend that, this whole darn thing is equal to 5. And I just want the distance from here over, okay? So basically, I'm gonna take this whole darn thing of 5, and I'm gonna subtract out this distance right there. Now, we just talked about in this first example, the distance from the y-axis over, that was whatever that x value was. So there it was 2, there was 1.7, there was 1, there was 0.4, right? So whatever that x value on that curve is, that's the distance from the y-axis over. So I know the distance from the y-axis over, that was x, but I don't want that. My capital R is the distance from the axis of revolution to that farther edge. I want this distance from here stopping at that curve. So I want the whole darn thing of 5, and I want to subtract out that x. That's what this distance is going to be. It's going to be 5 minus x. And so I would love for us to understand that, but sometimes it's kind of, hopefully you understand that. And I'll talk about it again in the next video. But then at some point, we could even just have memorized this just a little bit quicker. Anytime I'm measuring from this axis backwards like that, it will always be this number minus x. And so I always will start with that. And then sometimes we'll get to use that 5 minus x in my integral. Sometimes I'll need to change that right there. Even if this thing is right here. So if I move it right here to like x equals 3, well, then that distance is going to be 1 or 3 minus x. If I move it right here on top of it, the distance from there back, then it was just going to be 2 minus x. So if you move it a little bit closer, if I moved it right here where it was flush, then your little r would have been 0 because the axis of revolution, your closest would have been 1 the same. But if my axis of revolution is right here and it's flush against that shape like that, then that means that still that distance back, that whole thing would have been 2, but you're still subtracting out that x value, so that would have just changed that to be the 2 minus x. So it doesn't matter whether it's flush against it or way over here. When you're measuring from that axis backwards like that, it will be whatever that number is minus that x right there. So I just want to stress that a bunch, and then if you got questions, you can kind of let me know, and we'll keep kind of practicing that in the homework. But it's the same thing kind of over and over again. So if we keep working at that, we're going to be experts at that. Now, I'm not sure, this is kind of a little fun thing right there. Just if you take this shape and you revolve it around that x equals 5 line, you got this giant hole in the middle of that thing. I don't know if you guys ever played the game called Super Monkey Ball Deluxe. I don't know if it was for the Xbox or for the Wii or might have both, but I remember I'm just having flashbacks to the Super Monkey Ball Deluxe. It had all these mini games. You could shoot pool, you could play mini golf. It had the mini golf where these monkeys were like inside these spherical balls, and you would hit them and they would run and try and get into the hole, and they would do all sorts of different things there. So I just remember this one on the 18th green, you would like tap the monkey ball and it would like shoot up this plateau, and then way up here was like the hole where the golf ball had to go in. And so if you did it the right power level, then it would land on the green and you can kind of shoot it there. But if you got it wrong, then it just kind of fell into this giant hole, the giant abyss right there. So if you've never played Super Monkey Ball Deluxe, I highly recommend, man. It could be hours of fun right there. So, but anyways, notice that I got these set up, right? And so if this is a dx problem, I get to use that 5 minus x in my integral. But since this is a dy problem, I need to switch it, and I need to use the y version of that equation. So that's what we did at the beginning here, that x is equivalent to that square root of y over 2. Now, I know it seems like we're always changing it. I would advise you against just going straight to that. I would advise writing those down, starting with that, because we won't always need to change it. Sometimes people go straight to this, and then they mess themselves with the next section. They're switching stuff back, and then it's just off, all right? So just follow my thinking, do it exactly like I'm showing you here. That thinking is going to be perfect with this method, the next method, and it's going to be working out really well for us. All right. Then when I set this up using the this method, we're going to have the pi guy out in front. We're going to go capital R squared minus a little r squared. This is a dy problem, so I include my dy, and if it's a dy problem, I go bottom to top. What are the y's that take me across my bounded area? Or we're going from bottom to top, like you're doing a range from y equals 0 to y equals 8. So if I just ask you to set it up, then we're good there. Like I said, again, on the homework, you got to work it out the whole entire way through. All right, so let me just do a recap then, and I'll recap this at the beginning of the next section's videos as well. Our 4 big scenarios that we're going to constantly see when we're measuring stuff, and we have them all on the thing there, but a lot of times I'll just like to do a recap. Anytime we're measuring from the y-axis up, I'm sorry, from the x-axis up, that variable is always going to be y. Anytime we're measuring from the y-axis over, that variable is always going to be x. So I use the x when I did that first example, and I use that y when we did that second example. So those are two of the scenarios. And then the other two scenarios that you're going to constantly see is when you're measuring from an axis backwards. All right, so you got some curve and you're measuring from an axis backwards. It's always going to be, if this is x equals a number, this distance from the axis back will always be whatever that number is minus x. That's what we utilize right there. And if you have an axis of revolution way up here and you're measuring from that axis of revolution down, it's always going to be that number minus y. All right. So those are our four big scenarios. That's what I'm going to talk about. Will we have an axis of revolution over here and down here? Absolutely. But to me, that's just a little extension of these guys here, something that we already know how to do. So I'm just going to kind of save that when we encounter the other couple things in the homework. We could talk about those and we can make sure that we're setting those up properly right there. And I want to also mention that this little r, I said we're measuring from the axis back. It is still that number minus y, but see, this was from that 5 minus y equals 2, and then 5 minus y equals 2 still gave us that 3 right there. So those are the four big scenarios. When we would do the shell method notes, we'll highlight those again. So I'd love for you to understand those four big scenarios, but sometimes people have a little bit issue with that, so then it's just a little bit quicker for them when working out the problems where they have those kind of memorized right there. So hopefully that helps you come back and you can watch this as many times as you need to in order to prepare for a test or something like that. You just want to make sure you got that stuff down, and just good luck with that and practice as much as possible. Got to become experts at that, where we work these so much out that there's no way that we can mess these up there, whether you're having a bad day or you're feeling a little bit under the weather, that you're still going to be perfect with this. We want to practice as much as possible. I'm going to give you plenty of opportunities to practice this, so please do so and let me know if you got questions.